what I'd like to talk to you about is what Matroid has been up to for the past year. And the great theme that turned up as I was doing this is looking at how to turn machine learning research into products for industry. So a lot of research topics they have trouble when they get moved into products and into industry. So at Matroid, we're obviously taking cutting-edge computer vision research and putting it into the hands of folks that can use it in industry. We do that thinking very hard about what kinds of powers we're giving people. Before we do that, we have to make some analysis about whether it's the right time to move this machine learning piece of research into industry. And so there's a whole theme here that I'd like to discuss. It starts with adequate accuracy, which is a concept that seems super obvious, and yet I feel has been the reason that we've seen many failures in moving machine learning from university labs into industries. So I'll go over this concept, look at use cases that highlight that concept, give you a live demo of dealing with these issues, and a few more announcements. So what do I mean by adequate accuracy? So what I mean here is even if you have a 99% accurate model, that number doesn't really mean much unless you ground it in what's happening in the application that you're about to tackle when you're moving into industry. So even at 99% accuracy, if you have a 99% accurate detector or classifier, in the context of a recommender system, that's amazing. It's actually very unlikely that you'll achieve 99% accuracy in recommendations that you give people to who to follow on Twitter. Very unlikely. But the stakes are very low there. If you make a mistake, it doesn't matter. Some people don't get followed. Boo-hoo. No big deal, right? On the flip side, if you make a mistake while you're driving a car, if you don't detect the person, the results can be catastrophic. And in one case, even 1% accuracy is sufficient to move from research into industry. In the other case, 99% is not sufficient. You need 99.9999, several nines of accuracy. So this is the problem. So once you have a super accurate classifier, and you always have some measure of performance in a machine learning system. That's the typical difference between a machine learning system and a regular software system. You have to really figure out what is the appropriate threshold at which your product becomes useful before you even start building a product around it. So this concept is especially important when you're moving machine learning into products. There's a whole raft of other consideration when you're taking general software and turning it into a product. I'm not considering those issues at all. There are hundreds of books about it. There's so many guides and so on. We're not talking about general software. I want to really focus on what makes machine learning different, industrialization of machine learning different than other things. So this mischaracterization of how well we can do things in a classifier as compared to how well we need to do them is why there have been many broken promises in machine learning conversions into industry. So this is one of the reasons I claim that self-driving cars have been 5 years away for the past 15 years. Ever since the DARPA Grand Challenge, I was super excited. I was really looking forward to self-driving cars in 5 years because many researchers told me that. And of course, that hasn't been happening all the way till today. And even today, we don't have it. It's unclear when we'll have it. But I trust that Andre, who's going to talk to us about Tesla, he's a good friend of mine, and I haven't heard any timelines from him. But I think they are one of the leaders here. So we'll hear about where we are in that regard soon. And I think he has a very good grasp that he needs to understand adequate accuracy before he goes to market. So the same thing has happened in machine translation and speech recognition. My career started in around 2006-07 at Google Translate. And I look back, and there was 5 decades of research before, and something like 5 decades of failed attempts at building products around machine translation. Even today, there isn't a really good product for the goal of actual machine translation. You can't realistically give a document to a machine and have it translated well enough for any serious purpose. Around 2007, though, we achieved adequate accuracy as a research field where you could start using machines to do basic first pass translation and then start editing the document before you sent it out somewhere. So up until 2007, all that research wasn't even good enough to do a first pass attempt at the document and then have a human look over it, because the machine made so many mistakes, it was a waste of time to even do it, even do that. The translators would just start from scratch. So 6 decades of research, and from 1980 to 2007, there was a raft of machine learning startups that came and went. And because, why did they? It wasn't over-optimism, it wasn't false promises, it was, I think, a failure to look at how many years of research they needed to build a product that was useful enough that they could keep around. Same thing has been happening with speech recognition. Speech recognition has really started only working in the past 6, 7 years. So no one used to talk to their phone up until 6, 7 years ago. And now a lot of people actually use the voice search functionality to talk to their phone, to compose text, and to make searches. And this is, again, a new thing. It's happening because we achieved adequate accuracy for very short pieces of text when it comes to speech recognition. So if you're writing a text, or if you're writing a search query, if it's more than a few words long, it's likely the case that you won't make a mistake. If it's shorter than a few words long, it's likely the case that current speech recognition systems in English won't make mistakes, so there's usefulness there. If it makes a single mistake, the use goes out the window, because now you have to go and fuss around and backspace and correct and fix it, and you might as well just type the whole thing in the beginning yourself. So adequate accuracy is there. Don't annoy the user enough, and then they'll use your product. And that happened only after 6, 7 decades of research. And again, why was there so many failed attempts at this? I think it's because when people convert, they don't really think about this. Convert into an industrial setting, they don't really think about this enough, at least. Another one is computer vision. And I claim there's been a watershed moment in computer vision where there has been many, many applications suddenly reaching a point where they're ready for industry. So I claim we've reached adequate accuracy for object detection for millions of items. At least at Matroid, we have. And so we can take to market this ability to have what we call software-defined sensors. And what I'd like to do is walk you through some of these sensors and some of these use cases where we had to really think about it. Can we get that done in time? Can we get it more accurate enough? And then talk about the considerations about it. So the first one is a computer vision use case in worker safety. So in a construction site, you obviously want to be alerted if anyone's lying on the ground. There shouldn't be anyone lying on the ground in a construction site. This is something that if you were to hire someone 24/7 to look, you could do it, but they don't do that. Construction sites don't hire a 24/7 inspector to always be looking, unless it's a super, super big construction site. And so if you could have a camera just telling you, okay, look, I think there's someone lying down on the ground there, you could be saving a lot of people from injury, from hurt. You could be looking for people who are not wearing safety equipment. So if you're not wearing safety goggles, safety vests, and a safety helmet, you should not be allowed into a construction area. You could hire someone to check for that, or you could put one camera there that can check and green light. The adequate accuracy for that is you're being compared to nothing, right? No one is currently checking for this. So as long as you can provide value enough to an operator to not piss off that operator, then you can go to market. So as long as the operator can have some level of belief that when they get a notification that someone's not wearing a hard hat, they're in their construction zone, that has actually happened. So say you're not giving them, you give them a false alert maybe once every week. That's acceptable probably. You don't want to bother them more than that, because then you become the boy who cried wolf, right? And that's what stopped this technology from being deployed up to now. Computer vision wasn't even good enough to be at the level of, okay, make an error once a week. But now it is. And then the consequences for making a mistake, they're not that large. Okay, the operator gets a alert, and it turns out, oh, the person's wearing a hat, or wearing or something else that is including the fact that they're wearing a hard hat. So something like this is very reasonable. And a similar one is gas stations and checking for people smoking. It's illegal to smoke in a gas station. Obvious fire hazard. The problem there, though, is typical smoke detectors don't work outdoors, and gas stations are outdoors. The smoke dissipates too quickly. A typical smoke detector won't work, but a camera can very easily check that someone's putting a cigarette to their mouth, lighting it up, And again, the adequate accuracy there is that you don't piss off an operator, and it's currently not being checked for. And there are fires, and that's not okay, right? So if we can help that, we should. Another one is driver monitoring. Truck drivers are paid to go from one part of the country to another safely with their cargo, without hurting people, without hurting other cars. And if they're distracted in the cab while they're driving, that's not okay. You could have a buddy system where folks are buddied up, the drivers are buddied up with another driver, and they keep an eye on each other. That's unrealistic, right? Because that means you get double the cost for all of these truck driving companies, and they don't do that right now. So again, if you can check that someone's distracted, someone is looking down, or someone is on their phone in the cab of the truck, you can really help out. And this is yet another deployment at Matroid where we considered adequate accuracy. It turns out it's okay. Deploy it. One that is weirder is in restaurant kitchens. Restaurant kitchens have all kinds of guarantees about how they treat vegetarian food, how they treat allergens like peanuts and things like that. But who's checking? No one, really. If a cook accidentally reuses a vegetarian cutting board and puts meat on it, you're not going to know, right? And they don't have people checking this 24/7. They might have a supervisor walk in every long time, or maybe a health supervisor comes in every year. It's not being checked 24/7. But if you had a camera in the kitchen checking that, okay, this cutting board is meant to be for meat, this cutting board is meant to be for vegetables, don't use it. Don't mix the two, and you get a notification when it's false alert. Great, right? It's a sensor, software defined. The camera's already there. Almost all kitchens already have it. Makes sense, right? So this is yet another one. And adequate accuracy there is, again, very low. If you do it right, adequate accuracy is very low. And you have to be careful that you're not giving promises about, well, you still have to deal with the problem when the notification is given. Someone has to take responsibility and go and stop that cook or stop the food from being taken out. So you have to have in place procedure that stops the meat that is contaminated. Sorry, no, the vegetables that are contaminated from going out the door to the customer. This is another one, retail analytics, where retailers already do all kinds of analytics. They hire people to have clickers, and they click every time a customer comes in. They click every time. They do some level of analytics already. Retailers have analytics, and they're quite good at it. So in order to do better with computer vision and with a deployment, you have to beat that, right? So you have to be either more granular in the data that you can give them, or you have to be more effective and quicker. Somehow you have to be better. So in this case, we can do much, much more granular data. First of all, it can be 24/7, but then it can also be more granular in the form of aggregate statistics about age, gender, and just people counting. So these are aggregated statistics, not individualized, so that you don't violate anyone's privacy. So this is a situation where there has been a retail analytics industry for a very long time. You are being compared to something that is already there. This is one where probably you'll mistake what I'm going to say here. There's a railway operator. Obviously, they care about safety. And railways, people aren't supposed to be on railways. The first thing that comes to mind is, well, let's put a camera in the train and check for people on the line and stop the train if there's a person on the line. No. Why? We don't do that, and we will not do that, not anytime soon, because if we make a mistake in detecting a person there, they could get seriously hurt. So for that, you need the same level of a performant detector as a self-driving car. So we don't make that guarantee. We don't do it, but we do have cameras in trains, and we do check for other things. So we check for this particular railway operator wanted to check for garbage by the railway line, and for cars that are parked by the railway line, and they do want to check for people and where people congregate so that maybe they put up barriers and fences, but we gave no guarantee that there's going to be a feedback loop to the train to stop the train. It's just statistics and analytics after or during the train ride, but never a guarantee that will be the feedback mechanism to stop the train. That's key, because the difference between that project's adequate accuracy and what we're doing is huge. So you have to be very, very careful in your deployments as you're doing it. This one is one of my favorites. This is quite different from the others. This is a manufacturing use case. There's a roofing manufacturer that works with us. They produce roofing material at around 10 feet a second. So roofing material is coming off the line faster than anyone can really see and inspect. And when their factory has the smallest error, this roofing material comes out at a rate that is too fast for a human to see, and probably they'll only notice it after, say, half an hour of time has gone by. So half an hour of roofing material, 10 feet a second gets wasted, right? That's terrible. If you could have a sensor that could check for these anomalies in the roofing material, you could stop the line immediately. And what's adequate accuracy? The cost of making a mistake is that you stop the line for a short period of time, and then the benefit of being right is that you save, say, half an hour's worth of material. So if you stop the line accidentally, you're only going to be stopped for 30 seconds or so. If on the other side, if you correctly figure out that there's an anomaly and there's problem in the line, you save a lot of money. And so this is something that generalizes to almost all manufacturers. All manufacturers produce widgets, and they have to have a quality assurance step in there. If the quality can be checked for visually, you can add a sensor that can stop the line much more effectively now than if you had a human there. And that can generalize really, really effectively. Another set of generalized use cases is medical imaging that I'll talk about towards the end of my talk. Manufacturing, I hope, is clear, and we can talk about that in person as you would like. These IoT software sensors, software-defined sensors, is a lot of the use cases that we discussed already. And sadly, weapons, we don't work on weapons, okay? But every single weapon could get its target through CV. Absolutely terrified of that. The fact that that's possible now, and there's probably a lot of people working on it, worries me. It's something that we should be aware of. Like I mention it because it's a thing that we should be aware of, and everyone in this room should be aware of it. We don't work on it, and I'm sad to see that it's moving fast. So there's a wide variety of these customers that I could go into, and you're more than welcome to discuss these with us. But every time there's a very, very important analysis to be made, which is how much time do we need to get to adequate accuracy on this particular task? If anyone just tells you, oh yeah, CV is ready for industry, you should be very skeptical about that, right? CV in general as a whole, definitely not. There's so many unsolved problems. But CV is ready for industry in a lot of particular cases. And I think we've built a product that allows you to attack a lot of these particular cases with this in mind. And so one of the observations that you can make about what are the things that we're good at now and what are the things that are a little bit, they need more time before we take them to market is the difference between nouns and verbs. So in general, nouns, there are millions of them. Every year, Matroid gets better at detecting millions more things. When it comes to verbs, we only get better at 1,000 more things every year. So it's a much slower rate of increase, and that's because of restrictions in CV research and what's possible right now. And we're always at we keep abreast of the most recent Kaggle competitions, most recent competitions in general across universities to see how well actions are being performed. And it's definitely a slower rate of adequate accuracy, a slower rate of achieving industrial readiness than nouns. And so the key for product managers is, product managers are usually good at modeling a lot of things. They're often good at modeling revenue, but they're often not good at modeling the rate of change in accuracy. And when I say accuracy, of course, it could be whatever metric is more relevant for your task to go to industry. But you gotta model the rate at which you make mistakes, and then you have to ground that in the application that you're about to tackle, and then you have to see whether years of product development, or in the case of a product that already exists, whether days of product tinkering and just modifying will get you to a point where you can industrialize. And so this is a chart of modeling accuracy that I love, and this actually was what caused me to start Matroid is seeing this dramatic decline in error rate for the typical ImageNet task. And Andre was one of the creators of that, so his talk is coming up soon. I don't think he's going to talk about ImageNet, but it's nice that he's here. So this is the takeaway here, is that you should really thoroughly understand adequate accuracy before you deploy. And so what I'd like to show you is a little bit about what we've been doing to make it easier to achieve adequate accuracy and how we actually do it and deploy. So what we do is we own this whole product pipeline about all the way from integrating cameras or integrating large data sets from the cloud providers, providing that to you either in the cloud or on-premise, and then providing analytics, statistics, allowing you to search media, and allowing you to build detectors for what you need to detect, all in one place so that you can have a full feedback loop to achieve adequate accuracy. So you make some mistakes off of a video stream, you fix them, you redo the detector, you redeploy, and hopefully you have a better detector. You can get our help to do that, but generally we own this whole loop in order to bring the time to adequate accuracy down to minutes, not months. And that's why our slogan is exactly that. So I want to quickly remind you of what the product looks like and show you some of the new things that we have built in this regard. So here I'm monitoring with the product, I'm monitoring Bloomberg, and I'm monitoring it for a bunch of different things. I'm monitoring it for backpacks, emotions, objects, gender, and the US presidents, the past 5 US presidents. And this gets automatically this calendar gets automatically updated with events that have happened on the stream as they're happening. And there's a little bit too many events, so I'm going to deselect some of the detectors and just keep the objects detector. And this objects detector, while Oren was talking at 9:10 a.m., detected this car. It was tuned to look for cars. At 9 o'clock yesterday, it detected this scene. There's a very, very blurry car there. So this is able to give you real-time recommendations within milliseconds, so that you can, if you're in a factory or wherever you are, you can do whatever you need to do, and then you also get emails and so on. But then I can say, look, find me similar detections to this, and we'll go back through 3 years worth of Bloomberg, and we'll give you other times that something similar to this happened on Bloomberg. And this happened 9 a.m. yesterday, and so you can see it seems like this is something that you reuse over and over again. So it also happened at February 25th. Happened on July 1st last year, it happened June 18th, and so on, the exact same scene. And maybe if I want to focus on particular areas, I'll get what happened, this similar thing happening on Bloomberg at other times. So only this area, that exact thing shows up at, and takes up more of the screen on April 22nd in 2018. I didn't know that. That's kind of cool. I'm a little bit riffing here because I only just saw these this morning. I can look at maybe some of the cars down here. Probably I'll get cars and pedestrians that showed up on Bloomberg across years. This is scaled to search for years of video, and is really not that much video for Bloomberg. We've scaled this up to, we've handled data sets of up to 5 petabytes. So this takes a lot of just physical space to store 5 petabytes. And then being able to index that and query it in milliseconds is pretty cool. So here I'm searching for that flag that showed up, and I get a lot of flags that showed up on Bloomberg. So this came all from a detection that happened in the morning. And if I hit view recording, I can get a recording of that exact time as it happened. So this is something that is new. Typically, we had a clip that we would show you, a video clip of the event. And now there's this beautiful, infinitely scrolling video player that lets me watch live as well as change the time scale. So instead of just a little clip around the event, you get the whole thing. And I can change the time scale here as needed and say go to whatever other time I want and view the video at that point. So this is something that we need video players across the board because we want to be able to give feedback. We want to tighten that loop as much as possible. So we have to build video players in a lot of places. So once I have these detections, I can, of course, get analytics. I can get statistics. So I can ask for, say, statistics on gender. on Bloomberg. And actually, this was used last night in the Democratic debate by one of our customers in a very public way to give the breakdown of time given to the different genders in the debate. In Bloomberg, in this particular case, it's kind of funny that we're monitoring his channel and he's running for president. The Bloomberg channel is male-dominated. It is 2-to-1 male to female. I've shown this before, so we don't need to go over it again, but I can ask for analytics in real time as needed. So how do we do this, right? So we would like to be able to attack some of those use cases that I showed you. So maybe we attack the use case for the kitchen, where we're detecting whether there's contamination on a cutting board. To do that, we need a detector. We have the world's largest body of detectors, thousands of different neural network architectures, all underlying thousands of different detectors. And if you can't find what you're looking for there, you can make a new one. What I'm going to do is I'm going to make a detector for maybe minced meat and vegetables, right? Because I want to detect those two things on my cutting board. I'm going to go through this very quickly. It tells me, OK, I have a detector for this already. Do you want to use it? I don't. I want to make a new one. This is our wizard that you go through answering the questions. It's pretty self-explanatory. But once I finish the wizard, I land in the studio, where I have to give examples of what I'm detecting. So typically, we try and pre-populate this for you so that you don't have to do too much work in annotating examples. So this is some examples of vegetables that we already have. And this is some examples of meat that we already have. Now, I can go ahead and annotate these examples, and that's great. However, this is a kind of time-consuming thing. So this is a new feature that I'd like to show you is now you can add collaborators to this trivially. So I would say, OK, I want help in annotating this. I'm going to ask for help from Steven, who is one of our awesome engineers. He built this. He worked on this feature and built it. I just sent email to Steven saying, hey, come collaborate with me. His email is pending. He's in the audience right there, and he just accepted. So he's going to collaborate with me on this detector. And I'm going to say, hey, Steven, you should work on the vegetables. I'll work on the minced meat. So maybe I go in and I drop a picture of minced meat in my studio here. Oh. So I put in my minced meat photo here. It gets added. And then I can go in and I can look at the vegetables and see what Steven's up to. If you notice, Steven is actually, these bounding boxes, they're just appearing without me doing anything. There's another one right there that just appeared over this tomato. But hang on a second. So tomatoes are not vegetables, right? So, and another one showed up over carrot. Steven is doing that, but maybe he's not doing such a good job because he put a bounding box over the tomato, which is not a vegetable. Of course it is for this discussion because we're really looking for plant-based things. But maybe I'm not so interested in that. So I can look at who did what, there's a revision history. I can look at, OK, what's going on with the different taggings. And maybe I didn't like that tagging, so I remove Steven because, well, I'm going to fix that and get another tagging person. So in general, if you have trouble tagging, we'll now provide this to you. We have a small army of annotators that can tag data for you as well, and you don't have to deal with it. And of course, you can download the data as well. This is yet another new feature so that there's zero lock-in if you need to download that data. As Oren mentioned, this is almost a core part of building machine learning models. And as you can see, this product is point and click. And so we've tightened the whole machine learning loop very, very compact to minutes. And then it's also the case that we've lowered the skill level needed to deal with it. And all of that is in service to achieving adequate accuracy before deploying. So now that I have this detector, I can hit train on it, and then I can deploy it. I'm not going to train it right now because that's not the best use of time. Instead, what I'd like to show you is another detector that's been monitoring Bloomberg. This one is relevant to the other detector that was relevant to the food case. This one is relevant to the safety vests case. You'd like to figure out if a person is wearing a safety vest. So I have here an appearance detector, again running on Bloomberg because it's a public stream that I don't have to worry about privacy. To use there, we care greatly about about our folks' privacy, so I don't use streams that I can't show publicly. So this is an example of a stream being monitored, and I'm monitoring it for people's clothes. And here I've detected black upper clothes. I'm pretty sure that this is black upper clothes, and you can see that I can sense these different colors, and I can monitor. I can then deploy this. So maybe I want to. Once I train the detector, I get a screen like this. I want to deploy it. I say, look, I want to monitor, say the construction site. We actually have a construction site right next to our office. I don't want our parking lot monitor. I want our right. So we have a parking lot. That's not relevant. I want to use the upstairs cam. There we go. So in the upstairs cam, you can actually see the construction area. So this is a construction site right next to our office. We got the office, and then suddenly they tore down the building next to us. It's been very interesting watching that. So then I can say, look, I want to be able to detect people wearing vests or otherwise in this area. I can freeform draw an area, hit save, and say set a sensitivity for people from 94%, and hit submit. And when I hit submit, I get the calendar that was looking for folks' descriptions. This is Al Jazeera. I would like to get Bloomberg. And on Bloomberg, I have the appearance descriptor. And that'll populate this immediately or in a couple of seconds, and then I'll have the detections there. So once I deploy, I get these detections, and you get the idea, right? So we also have now detectors that will go down to the very joint of a person. So in a hospital, you don't want to be able to go to into a surgery room without having washed your hands. And in general today, actually, we have hand sanitizer all over the conference. Please use them. In a fairly sensitive environment like a hospital, you want to be able to make sure that people have washed their hands before they go in. And in order to do that, you would like to be able to detect every single joint that they have. So in this detector, we can detect every single joint that a person has, including their hands, their eyeballs, and everything around it. So here, if you have this above a sink, you can check that the person is washing their hands before they go in. This is a surgeon, this is a doctor, very key, right? It can happen that they forget. So let's go back to the slides and just some few more announcements. So as you saw, we have this whole loop. That whole loop is available either in the cloud or on premises in Kubernetes. The cloud locations the cloud is obviously available everywhere. The on-prem locations, those locations can be scattered. There can be hundreds of them. If you have, say, 100 hospitals that you'd like to monitor for hand washing, that's a nuisance, right? So a lot of our customers have asked for the ability to manage their cloud locations, manage their on-prem locations from the cloud. So this is a new feature that is also available today. It's harder to do a live demo for, but let's say I'm a person, my on-prem location is on the East Coast, the cloud location is on the North Bay, and I'm in the South Bay, and I want to check all of my hospitals because I have these compliant on-prem servers where the data stays private and the latency is low. It's as easy as a few clicks now to put in my cloud information into the on-prem server, and then that will populate a map on my cloud account. On my cloud account, I see all my locations. Once I want to really dive deep into a location, I just press a button to dive deep there, and I get to see it. So these are some of the software considerations that you need to make basic machine learning deployable. It's not super complicated, but it's definitely needed if you want to manage a large number of streams and if you want to really start showing value at a large scale. Another one is the ability to connect a larger number of cameras. So this is something where there's a standard called ONVIF. Cameras like Axis, Tyco, Pelco, and a few others support it. hundreds of different cameras supported, and you'd like to be able to register, say, 100 cameras all at once. This UI now allows you to do that using the OnRIF protocol. We have a few of those cameras outside in order to show you that. There's yet another tiny little thing, but if you're going to close the loop and repeat and repeat and repeat till you achieve adequate accuracy, you have to have these features so that you don't need a machine learning guy and you don't need a programmer guy. So that's the ability to connect. Both of these are new features that are available as of today. We're very proud of that. We've been working hard. So what have I shown? I've shown the ability to build your own custom detectors, visually search through billions of files in milliseconds, monitor millions of video streams in a few clicks. And that has resulted in the ability to have all these sensors that are useful in different contexts. You can't take one sensor and always expect that it works, but will work for you in order to make sure that we get you there. There was some discussion of interpretability in Oren's talk. We have the ability to tell you how important every single pixel was in a detection before you deploy it. So this is something where if you say, well, look, I think this is a fighter aircraft versus an airliner, we'll highlight the pixels that we used to make that detection. That's key in order to be sure that you're focusing on the right things. If you maybe create a car detector versus a person detector, your cars are taken in the nighttime and your persons are taken in the daytime, you might just train a daytime versus nighttime detector. And that is mitigated here by being able to see which which pixels were the most important for the detection. You also have the ability to do the PCA projection of the training examples to see where the model is confused. So the orange tinted here are the fighters, the blue are the other ones, and this area is the area of confusion. So this is something that lets you reduce any kind of doubt in your model before you deploy it. So that's model interpretability. There exists entire startups just for that. I'm not sure why. This is a feature here. There exists entire startups just for collaborating on training data. We have everything I showed you is available via an API. It can be integrated. There's an entire feedback loop. In order to build that feedback loop, we had to build video players galore. So I have video players to let me select training data. I have video players to play a video and then annotate it. Video players for infinitely long data. All of those places let you give feedback and retrain the detector. That has resulted in a growing detector library, and that Studio is there to support the detector library. Real-time streams and large collection search are typical deployment modes that are available with point and click. These are all, we're very proud of these, and it's the kind of thing that takes it to, it's the kind of thing that really is needed in order to get these going. And then there's all these fancy, much more fancier things that is hidden in the product under advanced menu tabs, like the ability to import a TensorFlow saved model, which we're going to hear about, well, we're going to hear about TensorFlow right after this talk from Megan Cacholia. And if you have a regular TensorFlow model that's already been saved, you can just import it, and then you get all of these features from the get-go. There's even more visualizations through TensorBoard. There's the ability to auto-label and use other detectors to tag your data. There's a tremendous amount of work that you can do here. This is a new service that we've been doing where we will compress models based on what the customer needs. So everyone knows that these, we have thousands of different neural networks. Some of them have very high compute requirements. And yet the customer wants to deploy them on, say, a fairly weak AI chip, something on the edge, low power, very low wattage. And they would like to be able to say, well, look, that sensor that I built on Matroid.com, I'd like it here. So we have the ability to compress that. Using these techniques, we will do parameter pruning, sharing, and quantization. Those are the easy things. Lowering factorization gets a little bit more advanced, where you have a matrix and you bring it down to a few factors that are much smaller and cheaper to compute, as well as knowledge distillation, where you have a really fat model teaching a very, very small model. And the reason you would want to do that is because you can use essentially an infinite amount of training data to get labels from the fat model, teach the student model, and the student model can learn at a tensor that is not just the output labels of the fat model, but a tensor that is further inside. So that allows us to compress very large models into much smaller models. Along with these other tricks, we can typically provide a week-long SLA to take a model that might be overly expensive and do this for a very weak chip, maybe from 10 years ago. For example, we did something like this for Intel, where they had a camera and they wanted a detector on there that was too expensive. We brought down its complexity and we deployed it successfully. So I promised to get back to medical diagnostics, and this is the last thing that I'm going to show you today that is very, very close to my heart. So we know that achieving adequate accuracy for replacing doctors is far away. So I claim this. Some people don't. Some people will tell you, well, radiologists are going to be out of a job in 5 years. I don't think that's true. I don't think that's true. However, we are going to augment the hell out of medical imaging devices in the next, right now. So X-rays, OCTs, MRIs, all of these can come with a diagnosis hint, right? That you tell you, well, look, you should be looking at this area. You should be looking at, there's a potential fracture here. Doctor, look at that area. Don't miss it, right? I wouldn't be surprised if someone in this room had a situation where they got some medical imagery done and the doctor missed something in it. That should be mitigated, right? You can mitigate that by providing diagnosis hints and aids to a doctor. The adequate accuracy for that is much lower, right? Achieving a situation where you can provide hints it's a much, much easier adequate accuracy bar than it is to replace a doctor. To replace a doctor, you need, I claim, almost full AGI. So that's not going to happen for a long time. But you can augment these things, and we did it for OCT. So with my own doctor, we are able to detect glaucoma in the human eye better than humans, or on par with humans. And so this is, what is an OCT? As a reminder, an OCT is a 3D scan of the eye. So you get a scan of the eye. It looks like this. This is the cell layers at the back of the eye. And typically glaucoma is diagnosed by looking at this layer that is just right there. There's a thin cell layer. If that cell layer gets too thin, you start losing peripheral vision. So the world looks like it's like a tunnel, and slowly it becomes more and more tunnel-like till you just have a pinprick of a vision, and then that goes away too. And this is a very, very common disease that affects a lot of people. The way to track it is to track how thick this cell layer is using an OCT scan. However, there's all kinds of cases where that cell layer is pretty much entirely gone, and yet the person still has sight, and the doctor can't really now have a way to track the progression of the disease. Some people naturally have thinner cell layers there. Some people have thicker cell layers. There's a lot of variation. And really, it's something after the cell layer goes away, even our most advanced diagnostic tools are amiss. So what we've done here is we've trained a model that uses the whole scan. Of course, we checked using saliency maps and using the explainability that the model is focusing on that cell layer. But then we went a step further. What we did was we took away that cell layer and saw if the model could still work. So we took away everything that cell layer, handpicked that cell layer out. So we know every single picture that we have doesn't have that cell layer that doctors use and the current OCT machines use. And we kept just this deep area in the eye called the lamina cribrosa. That area itself turns out to have enough diagnostic information that you can still do fairly well. And so putting all of that together, we can beat a human looking at OCT, and we can do as well as a human when the whole thing is there. And we can start giving scores to this area of the eyeball that was traditionally ignored by doctors. That's very valuable if you've lost that cell layer and now you're in a situation where you don't know how far your disease has progressed. If you fix a model, you can actually start tracking the score of that model and get another diagnosis aid as to whether you're getting worse or better. And so this is a rigorous ROC curve for what I'm saying. These two dots, the green and the red and the green, are other studies that people have done to evaluate how effective human doctors are at detecting glaucoma. Those are plotted here. And as you can see, one of our ROC curves beats them. And these are different data sets that we collected through different hospitals. We have the world's largest data set for this. We've gathered it through Stanford Hospital, Nepal, India, and Hong Kong. We can now say that we beat a human doctor at it. that doesn't mean anything because we're not going to replace a human doctor. We just can provide hints that are about as good as a human doctor. And what we can do now is we can go in and look at areas of the eye that were ignored before. So it's like a whole new set of information for doctors to treat this disease. This is pushing the boundaries of medicine. It's not just providing hints to a doctor. It's actually giving new tools that they can use to help people, which is just, I love that, right? And this is just joint work with my own doctor at Stanford, with Irfan, a Matroid intern, and with Surya, who's also at Stanford. So this is the kind of work that very clearly indicates why we should be working on these problems. And we think very, very hard about all those use cases that I showed you. We consider the privacy implications. We consider the security implications. These are things that I lose sleep over because of the sensitivity of the tasks. They're not easy to figure out which of these you should be doing and which of them you shouldn't be doing. One line that we have is weapons, but it's not really clear where the line should be. That's something that is being actively thought about and I think about all the time. And if you would like to work with us on these interesting problems and think about these issues that are in your face when you have to work on them, we'd love to work with you. I love working for the Matroid team. We'd love to work with you on these kinds of problems. Thank you. We have time for maybe one question. Yes, sir.
Questions regarding the medical imaging processing.
Sure.
In most real-world case, you will find a small set of label data. And then you can collect a lot of unlabeled data. Do you guys have any solution or have any experience how to using a small set of label data and trying to take advantage of unlabeled data? Thank you.
Yes and no. So unsupervised, it's actually not that hard to gather labeled data. So maybe you need 1,000 examples of one problem versus another. With the tool that we have, it takes a day. If you put a doctor and you pay them for a day, that's often enough. I don't know where the person went. That's often enough. And in the case of unsupervised learning, helping you achieve adequate accuracy, I don't think that's quite ready yet. So that's one of the situations where I love the research there and I love seeing the progress, but nothing beats supervised learning. When it comes to these problems, supervised learning is hands down the right thing to use, and we're focused on getting people the best solution.
I totally agree with you about supervised learning. Actually, what I'm asking for is the raw data you input into the system. Initially, if you do this, you might have 50,000 label data, but you have 500,000 unlabeled data in my case. So yes. Can you, yes. I don't mind doctor getting to evaluate, but they just don't, it's not cost or time effective.
We do have that, so there's a bank of pre-trained models that we build off of. Some of those pre-trained models are autoencoders that have been trained. And so the training I didn't talk about, but the detector training involves a neural network architecture search. It involves trying different transfer learning techniques. It involves training networks from scratch, and we try all of those. And if you have a bank of unlabeled training data that is substantial, we can use that in either an autoencoder or other ways to provide features that could then be tested on a smaller set of supervised data. But there isn't a way that I am comfortable deploying things in hospitals without some level of supervision. So you need some level of supervision, and yes, you can use that bigger data set in order to help bootstrap from the supervised examples.
Okay, thank you.